Hello, and welcome to the video lecture for topic 9, cycloalkanes, ring strain, and cycloalkane conformers. So, cycloalkanes, much like our open chain alkanes, can adopt different conformations, and these conformations, similar to our open chain alkanes, have both torsional and steric strain considerations. But in some cycloalkanes, there is a third type of strain that we need to take into consideration, which is called formally Bayer strain, but more casually is known as angle strain. And I will refer to this as angle strain for the purposes of our class. And now angle strain is exactly what it sounds like. It is strain that occurs within a molecule that is a result of a bond angle either increasing but more frequently decreasing from its preferred value. Right, and from the value that Vesper would predict for that particular hybridization. Now this type of strain is going to be most common in 3, 4, and 5-membered rings. And so we're going to take a look at those first. So we'll begin with 3-membered rings. So the simplest 3-membered ring is cyclopropane. Now, when we draw cyclopropane as a planar molecule, right, we would think that the bond angles that we have would be 60 degrees. Even though this carbon atom, and in fact all 3 of these carbon atoms, are sp3 hybridized, and so our preferred bond angle would be 109.5 degrees. And so you can see how there's a great deal of strain, there's a very large increase in potential energy for cyclopropane if it were to actually adopt this 60-degree bond angle. Now, cyclopropane is very special in how it deals with this, and what it actually does is it deforms this carbon-carbon bond in order to alleviate that strain. And so if we were to do a valence bond diagram for cyclopropane, what we'd see is, as opposed to a linear carbon-carbon sigma bond, what actually happens is that sp3 orbital bends out, right? On each of these carbon-carbon bonds, those sp3 bond angles bend out. And so it deforms this bond angle, right, from being what we would predict 60 degrees based on a planar geometry. It's not quite 109.5 degrees, which would be preferred. It's actually pretty close to about 103 degrees, right, which alleviates a significant amount of that angle strain that we see, but it also makes this sigma bond very weak. And so cyclopropanes are very reactive because these sigma bonds are so weak because of this angle strain that exists in the molecule. Now, if we were to look at down one of these carbon-carbon bonds, even though it's kind of bent, right, where those two sp3 orbitals overlap, what we would see in a Newman projection for that is that it must have this eclipsed conformation for its hydrogen-hydrogen bonds. And so now I'm just going to kind of put out, there's our third carbon, and so our other 2 hydrogens on this back carbon are actually eclipsed with the 2 hydrogens on the front carbon. And so we have a significant amount of torsional strain because this occurs with all carbon-hydrogen bonds on the same face of that cyclopropane. Right? So all 3 of the carbon-hydrogen bonds, if we were to draw this one in, all 3 of these are eclipsing, and all 3 of the upper hydrogens are also eclipsing each other. So we have a significant amount of torsional strain that comes from these eclipsing interactions. Also, all 3 of the carbon-carbon sigma bonds are eclipsing each other, and so we have a lot of torsional strain there as well. So cyclopropane, very, very, very high strain energy in this molecule. If we move now to the next largest cycloalkane, right, a 4-membered ring, so cyclobutane now, in a planar drawing, the way we normally put it down on a sheet of paper, cyclobutane, we would think, has 90-degree bond angles. Now, where cyclopropane bends its sp3 sigma bonds to relieve that angle strain. What cyclobutane does is a little bit different. It actually pushes one of the 4 carbon atoms out of plane with the other 3 and kind of bends it a little bit. And so if we were to draw more of a perspective diagram versus a planar diagram for cyclobutane, what we'd see is it really adopts a conformation that looks more like this, where we can take and imagine that 3 carbon atoms are all in the same plane and 1 carbon atom gets pushed down out of it. Now what this does is it relieves the torsional strain of eclipsing bonds. So here now if we put in our hydrogens, this now relieves the torsional strain because the carbon-hydrogen bonds are no longer eclipsing each other. However, it does it at the cost of increasing angle strain. So these bond angles now are approximately 88 degrees. The increase in angle strain we get is actually less than the amount of decrease in torsional strain. So we win on the torsional strain side by a significant amount of energy, and we pay a very small price on the angle strain side. Torsional strain, we gain a lot of torsional strain relief, and we pay a very small price of angle strain increase. And so cyclobutane, right, it can adopt this kind of puckered or folded conformation, as we call it, in order to, relieve the majority of the strain. And so if we compare, but we still have a good deal of strain in both of these systems. So in cyclopropane, if we sum up the total angle strain, right, and again, if we total the total strain energy, so this is angle strain, torsional strain, and steric strain in a cyclopropane, what we find is we can assign a value to the strain energy of cyclopropane is approximately 115 kilojoules per mole. Now, if we sum up the total strain in cyclobutane, again, this is angle strain, torsional strain, and steric strain for cyclobutane, we find that it's actually pretty close to cyclopropane at about 110 kilojoules per mole. So these are both very, very highly strained systems. And in fact, cyclobutanes are only slightly less reactive than cyclopropanes, and that high reactivity for both of these systems is a result of strain relief when these molecules undergo a reaction, and especially when these molecules undergo a reaction that will open up the ring to relieve the different forms of strain that exist in them. So finally, let's take a look at cyclopentane. So for cyclopentane, if we draw out its structure as a planar molecule, we would think, right, that this cyclopentane should have bond angles of approximately 108 degrees. That's what we expect, right? In fact, cyclopentane is not a planar molecule, and it adopts what's called an envelope conformation. So that envelope conformation places 4 carbon atoms in the same plane, and then lifts one of those carbon atoms. Excuse me, let me get a better drawing of this. So puts 4 carbons in the same plane, slightly better there, right? 4 carbons in the same plane, and then lifts 1 carbon atom out of the plane, right? This again relieves almost all of the angle strain that we find in this molecule, and we find that it has true bond angles that are about 109.5, just like we expect for tetrahedral carbons. So and it also reduces the overwhelming majority of any torsional strain that would occur in this molecule by eclipsing carbon-hydrogen bonds. And so whereas cyclobutane and cyclopropane have strain energies above 100 kilojoules per mole. Cyclopentane is actually a relatively stable kind of a system, where its strain energy is only, its total strain energy, this comes from, again, torsional, steric, and angle strain, is only about 26 kilojoules per mole. Right? And so now we see, as we increase ring size, we are reducing the overall strain energy in the ring, and we do that in a series of different ways. Cyclopropane, we have these very weak bent sigma bonds that enable the carbons to adopt 103-degree bond angles, as opposed to 60 if it were planar, but we have a lot of torsional strain in the system because of all of the eclipsing carbon-hydrogen and carbon-carbon bonds. In cyclobutane, we still have a lot of strain energy, 110 kilojoules per mole, but this is because while we relieve torsional strain by adopting this puckered conformation, we increase the angle strain slightly and end up with bond angles of about 88 versus 90 in planar. Finally, right, cyclopentane, we get those 109-degree bond angles that are desirable for a tetrahedral carbon. Very little torsional strain in this molecule. Very few of the carbon-hydrogen bonds are eclipsing each other. We only have a few carbon-carbon bonds eclipsing each other. We have lots of gauche interactions here, which is very good. And our total strain for cyclopentane is reduced to about 26 kilojoules per mole. Let's now move on and take a look at cyclohexane, which is going to be the cycloalkane that we work the most with this semester and next semester. Now, cyclohexane is the most stable of all cycloalkanes. It has the lowest strain energy out of any possible cycloalkane ring size, or really any ring size that you're going to encounter in organic molecules. And a really common phrase that you'll hear a lot of organic chemists say is, nature loves a six-membered ring. And the six-membered ring is very unique and occurs, and we're going to see it very, very frequently, both in Chem 201 and Chem 202. Now, if we take a look at a planar rendition of cyclohexane, we'll see that if we were to consider what the bond angles should be, based on this planar depiction, we would think that these carbon-carbon bond angles would be at about 120 degrees, right? It looks like it's sp2, but we know that all of these carbons are sp3 hybridized. And so we are looking for these carbon atoms to have 109-degree bond angles around between each of their electron domains. And in fact, we'll see right now that it does adopt these 109 bond angles, because a six-membered ring can adopt a very special conformation that's known as the chair cyclohexane, or the chair six-membered ring, which in a perspective drawing looks something like this, where one of the carbon atoms sits above a plane for the other four, and one carbon atom sits below the plane for the other four. This allows this cyclohexane to adopt 109-degree bond angles for all the bonds that exist in the molecule, both the carbon-carbon and carbon-hydrogen bonds. So we have full 109-degree bond angles. And now, so we've eliminated all of our angle strain. The other consequence of this is that it eliminates nearly all of our torsional strain. And so if we were to put in our hydrogen atoms with our appropriate bond angles, we would see that we have almost no eclipsing interactions. So I'm just going to put in a few of these hydrogens to demonstrate that. At this point, you really want to start using models to get a sense for how all of these atoms and bonds and bond angles work together. And chair cyclohexane conformers are going to be a very large part of what we're going to consider in the coming weeks. And so it can adopt what's known as this chair conformation, where we have very little to no torsional strain, very little to no angle strain. And so if we do a strain analysis on cyclohexane, the same as what we've done for our cyclopentane, cyclobutane, and cyclopropane, we see that it has about approximately 0.1 kilojoules per mole. And in a relative potential energy diagram, cyclohexane versus cyclopentane, butane, or propane would be our reference mark of 0 relative potential energy. Everything else has a higher relative potential energy. Even 7-membered, 8-membered rings, if we increase past 6, we begin to increase potential energy again. Not as drastically as for smaller cycloalkanes, but still significantly relative to cyclohexane. So, drawing these chair cyclohexanes is going to be something we need to do a lot. It allows us to determine which conformer of the two is going to be which conformer is the most stable when we have a substituted cyclohexane. And so I'm going to redraw this now, and I'm going to start talking about some of the terms we use to describe the different conformers and the different positions of the atoms within the molecule. So, when drawing a chair conformer, we want to start off by having two lines that are parallel but offset from each other. These two lines are going to determine for us, fix those up a little bit, are going to determine for us which direction our remaining two carbons are going to be. So here I've drawn my two lines. That's for my center 4 carbons. And then now we draw two lines to give a carbon up and two lines to give a carbon down. So this is our basic carbon-carbon bond framework for a chair cyclohexane. We could also draw it the opposite way, where we put one carbon down and one carbon up. These are both chair conformers, and while this one up above isn't super beautiful, it's still a reasonable drawing. From there, we have very specific terms that denote the position of substituents in these chair conformations. And these two terms are either axial or equatorial. An axial substituent will always point either straight up or straight down. So how would that look? So for our upper drawing, we would have an axial position here, an axial position there, and an axial position there. And then we would have an axial position up, another axial position up, and another axial position up. And this use of up and down is just exactly the way I said it. For the 3 axial positions that are pointing below the plane of the ring, we would denote those axial down. And for the 3 that are pointing above, we would denote those axial up. To do this same process on our lower cyclohexane conformer, here we would have an axial up, another axial up, a third axial up, and then 3 axial down. That leaves us 6 more substituents that we need to put on the ring. And those are all going to be denoted as equatorial positions. And the name equatorial comes from the fact that they roughly will lie in a plane that is the equator, so to speak, of our cyclohexane. So here we would have an equatorial position. Here's another equatorial position, our third equatorial position, our fourth, our fifth, and finally our sixth. Now, similar to how axial positions can be noted up or down, our equatorial positions can also and are also described as either being up or down. So if I have an axial up at this carbon, my equatorial is by definition down. Same here, if I have an axial down at a carbon, my equatorial group at that carbon is by definition up. So we will always have at each carbon one substituent up and one substituent down. We will have one substituent axial and one substituent equatorial. And based on the conformer, we can make this combination, or we can set these combinations of axial up versus axial down, and equatorial down versus equatorial up. So that's how we refer to our chair conformers and the different positions within our chair conformers. Now, for plain cyclohexane that only has hydrogen atoms on it, either one of these two chair conformers really has the same energy. There's not much difference between them. In one, we'll have 3 hydrogens up, 3 hydrogens down, axial up, axial down, excuse me, and 6 hydrogens equatorial, and in the other we'll see the same thing. However, as soon as we replace one of those substituents with something bulkier than a hydrogen, we are able to make a determination as to which conformer would be more or less stable than the other. So let's take a look at how that works right now. So I've left here our core cyclohexane system denoting axial up and axial down for each of the positions of the substituents so that we can have it as a reference as we move into this new exercise. So we'll begin by looking at a planar cyclohexane molecule on which I'm going to put a methyl group on a wedge. So there's my methyl group on a wedge. Now, if you'll notice, all that methyl group and wedge tells us is that the methyl group is up. It doesn't tell us whether it's axial up or equatorial up. And so we need to draw the two chair conformers and see what's going on in both of those systems. So we'll begin with one chair conformer like this, and I'm going to put my methyl group on this carbon here. It's up. If I refer over here, that means I'm going to put my methyl group axial up. Excuse me. Which means I have a hydrogen down equatorial. And I'm going to number this, keep this carbon in mind. What we need to consider in this situation is what's known as a 1,3 diaxial interaction. And so we can see here, if I number this carbon 1, that would make this 2, and this carbon 3. We see that there's this potential interaction between the axial substituent at carbon 3 and our methyl substituent at carbon 1. Now here in this methyl cyclohexane, because I have a methyl group and a hydrogen interacting, there's very little steric interaction between these two, but there is some. And as this methyl group gets larger, or this hydrogen group becomes something bulkier, so if I switch this to a T-butyl and a methyl, that 1,3 diaxial interaction produces a lot of steric strain in the molecule. Now let's take a look at what happens if I do what's called a ring flip on this. Now a ring flip converts between two different chair cyclohexane conformers. Essentially what I'm doing is I'm taking this carbon labeled 1 here, pulling it down, and taking this carbon, that would be 4 here on this side, and pushing it up. This is going to result in a complete switch of axial and equatorial positions. So now drawing my new chair conformer, again here now I have carbon 1, 2, 3, and 4. My methyl group was axial up in this situation. However, now at carbon 1, my axial position based on this drawing would be down. And so my hydrogen is down, so I would need to put my hydrogen in that axial position. My methyl group is up axial here. The other position is now up equatorial in my lower conformer. So our methyl group is now equatorial up. A ring flip only changes a group from being axial to equatorial, but it doesn't change whether a group is up or down. So that means for methyl cyclohexane, there are two potential conformers. If we have a wedge, our methyl group could either be axial up or equatorial up. The stereochemistry implied by that wedge remains constant. Up will always stay up, but we can have two conformers, one axial up or one equatorial up. Now if we look here, because this methyl group is now in an equatorial position, if I draw my substituents at the carbons directly adjacent, I see that I have a 60-degree dihedral angle between this methyl group and this hydrogen, so we don't have any torsional strain there. And we have removed now that unfavorable 1,3 diaxial interaction between the methyl groups and the hydrogens at the carbons, either of which could be denoted 3. And so now, since we've removed this potential steric interaction, and we've kept our potential torsional interactions the same at these 1,3 positions, we now can see that this lower molecule, where I have placed the bulky group in an equatorial position, is actually lower in energy than if I have this group axial. And we're going to find that tend to be true. Bulky substituents on a cyclohexane always prefer an equatorial position. Whether they are equatorial up or equatorial down isn't as important as the fact that they are equatorial versus axial. So we've looked at a single substituent. Now let's change this up a little bit and see what happens when we have two substituents or more. So again, when we're going to look at more than one substituent, I'm going to start off just with a planar representation of my cyclohexane. And now I'm going to use a couple of pretty bulky substituents. I'm going to put a tert-butyl group off of this carbon, and I'm going to put an isopropyl group off of that carbon. So now these two groups have a trans relationship, one up and one down, right? And they're at the 1 and 3 positions. So now let's draw our first conformer. And so we'll begin with numbering, so we'll call this position 1, 2, and 3, where our large substituents will be. And now we can arbitrarily set in, we'll call this our carbon 1, this our carbon, this our carbon 3, and let's see what the two conformers would look like. So at carbon 1, we have a tert-butyl group up. If we refer back to this guiding diagram for the conformer we're drawing, we'll see at carbon 1, our group would be axial up, and at carbon 3 down would be an equatorial down. So here now at carbon 3, we have our isopropyl group equatorial down. And we'll put in our remaining hydrogens that would be attached to those carbon atoms. So we see here in this conformer, we've placed the much larger group in an axial position. And that's going to have a stronger or a larger steric strain in this 1,3 diaxial interaction between the tert-butyl groups and these hydrogens. And so if we look at our other chair conformer, we're now going to pull this carbon down, we're going to push carbon 4 up, and see what that looks like. So again, here's carbon 1, carbon 2, and carbon 3. At carbon 1, our tert-butyl group is still up, but now that we've done our ring flip, our tert-butyl group is equatorial up. And at carbon 3, our isopropyl group is still down, but it is now axial down, with our hydrogen at carbon 3 equatorial up, and our hydrogen at carbon 1 axial down. Here now we've placed the bulkier of the two groups in an equatorial position. And again now we always want the bulkiest group in the equatorial position. This would be the more stable conformer. The ability to do this sort of analysis is going to be a big component of the next few weeks, and so being able to take a planar representation and convert it into a chair structure or a chair representation, being able to create both conformers is a skill that you're going to need to develop. The last thing that's useful for us to do is to make what I like to call a double Newman projection for these cyclohexanes and do conformational analysis in that way as well. When we do a double Newman projection for a cyclohexane ring, we're sighting down two parallel bonds simultaneously. So for this specific molecule and this specific conformation that I have circled, we would sight down this bond and this bond simultaneously. Let's take a look at how we would actually go about drawing that. So again, I'm going to have two Newman projections that are connected to each other. And that starts off by drawing my two circles. So here on this circle, it's carbon 3 that's in the front, and in this circle, it's carbon 1 that's in the front. Which means if I continue this numbering scheme, the back carbon behind carbon 1's Newman projection is going to be carbon 6, and the back carbon behind carbon 3 will be carbon 4. Now, I'm going to fill in the rest of my hydrogen substituents. There's carbon 4's hydrogen substituents, and the hydrogen substituents on carbon 6. Now, as I look down this 3-4 bond, viewing from carbon 3 towards carbon 4, I see that on carbon 3, I have an isopropyl group going down like this, and a hydrogen atom coming up like this. Now I have this carbon 3, carbon 2 bond going up in this direction. There's carbon 2. We're going to ignore the substituents at carbon 2, but we see that carbon 2 is now connected going down to carbon 1. If I do my analysis for carbon 1, I'll see that I have my tert-butyl group going up, and I have my hydrogen straight down. That takes care of the 3 carbon atoms that are the front of the molecule. Now for the 3 carbon atoms that are the back, we would repeat this same process. We would start with carbon 4. On carbon 4, we see a hydrogen atom axial up, and we see a hydrogen atom equatorial down. Now, from carbon 4, we have a sigma bond going to carbon 5 in the down. So there's our C5 down. And our back carbon, carbon 6, is also a sigma bond down to carbon 5. Finally, our two hydrogen substituents on carbon 6, we have a hydrogen atom up and axial, and then down and equatorial would be our last hydrogen atom. And so now here we can see that our diaxial interactions, 1, 2, 3 diaxial, are between this hydrogen and this isopropyl group, and that our big, large, bulky T-butyl group is spaced in an open region where it doesn't really have any steric or torsional interactions. And so this is a second way that we can begin to do conformational analysis. If we wanted to do a ring flip on this from one conformer to the other, we simply pull C2 down while we push C5 up. So let's see what the consequence of doing that would be. We're going to keep carbon 3 as our front carbon on this side and carbon 1 as our front carbon on this side. But when I pull C2 down, that's going to rotate my hydrogen and isopropyl groups in this direction. So there's carbon 3, there's carbon 1, both in front. I have now pulled C2 down, and that rotates my isopropyl and hydrogen groups. My isopropyl is now here, down to this side, and my hydrogen is now up in this direction. Similarly, when I pull C2 down, the effect on the tert-butyl and hydrogen on carbon 1 is the same. They rotate just in the opposite direction as how the substituents on carbon 3 rotated. So this now takes my tert-butyl group and pulls it up. So there's my tert-butyl group up. And it pulls my hydrogen a little bit in this direction, down, and to the side. Now we're going to do the same thing with C5, except this time we're going to pull C5 up. So that means C5 now goes up here in this direction. And the consequence of pulling C5 up is to take these two hydrogens and turn them this direction. So now my top hydrogen goes here, and my bottom hydrogen goes here. Similarly, on carbon 6, which is behind carbon 1, when I pull C5 up, my two hydrogens rotate in this direction. And so I have one hydrogen here, and now one hydrogen down here. If we now try to assign axial and equatorial positions to these 8 substituents that we've dealt with, we can see how a ring flip changes up and down, axial equatorial, but doesn't change up and down. So we'll start with this isopropyl group, and we can see here it is axial down, whereas here it is now equatorial down. Axial switched to equatorial, but down stays the same. We can continue this process. Here we have a hydrogen that's equatorial up, and that same hydrogen is now axial up. The hydrogens on the back carbon, carbon 4, we started with one axial up. That hydrogen rotated this direction to become equatorial up. Our hydrogen that was equatorial down has now been rotated to become axial down. And the same thing can be seen for the substituents on carbons 1 and 6. Our tert-butyl group in this lower Newman projection began as equatorial down. Same here, equatorial down. Now, equatorial up. Now it is axial up, same as it is here. And this was equatorial up. our hydrogen on carbon 1 moved from being axial down to being equatorial down. And then our hydrogens on carbon 6, we had axial up, which is now equatorial up, and equatorial down, which is now axial down. And so we see that a ring flip only changes whether a substituent is axial or equatorial. It doesn't change whether a substituent is up or down. So this process, creating chair conformers, evaluating the stability of substituted cyclohexanes, is going to be a big part of what we're going to do over the coming week. And this ability to convert into a double Newman projection gives us a further skill or a further technique for doing a conformational analysis on cyclohexanes. Now, I want to make you aware that this video just provides one component of what you're going to need to learn for topic 9. It's got some. There will be overlap with your reading, but your reading will provide you information that's not here in this video lecture. Of special importance is Table 3.2 in Sorrel, which talks about delta G values for specific substituents, whether they're in an axial or equatorial position on a cyclohexane ring. That is going to be one more tool we use in making these conformational analyses. Finally, the worksheet for topic 9 has information, again, that overlaps with the video lecture and with the reading, but includes further information that won't be present in the reading or in the video. So while each individual component does provide you some information, and there is overlap between the three, each one will have some information that the other two do not. So I advise you to make sure that you have a solid understanding of the reading, you've watched this video lecture and understand the concepts herein, and that you go through the entire worksheet to make sure that you have a solid understanding of the information presented there as well that isn't covered by the lecture or the reading. All right, thank you very much. I hope you've enjoyed this video lecture. As always, if you have any comments, please feel free to stop by for office hours, bring them up in lecture or in conference, or make a Google Calendar appointment and see me personally. Have a good day.